Hi, my name is Matt Duff, and today I'm going to give you a few tips for picking component values for your Sallen-Key filter. So up here on the board we've got the Sallen-Key filter and a gain of 1, and here we've got the two equations for that Sallen-Key filter. So we've got the pole frequency or the natural frequency, and we have the Q or the peaking. Now you'll notice we've got two equations, but we've actually got 4 variables that we can play with here. So that means that we actually have 2 degrees of freedom. Now, you can burn those 2 degrees of freedom by setting, say, C1 equal to C2 or R1 equal to R2 or other tricks to make the math easier. But by making the math easier, it doesn't actually help your electrical performance of your circuit. Now, we've got this nice tool for you, this Filter Wizard tool up on the web, and that tool does the math for you. So we figured, well, we'll try to find ways to make the electrical performance better. So one way we use these degrees of freedom is we give you the option of choosing the trade-off between the resistors and the capacitors. So you can pick either big resistors and small capacitors, or you can pick big capacitors and small resistors. Now, when would you want to use one versus the other? Well, let's say you've got something that's not very good at driving your filter, then you're going to want to have big resistors so you don't load whatever's driving that. Or let's say you've got a low power amplifier, you'll also want big resistors so that those resistors don't load the amplifier. Another reason why you might want to have big resistors is as we've learned in another video, the Sallen-Key configuration has this issue at higher frequencies where the output resistance of the amplifier degrades the performance. And so the higher the resistance that you have here, the less of an impact that issue is. So that's some advantages for having big resistors. Some advantages for having small resistors is it'll help your DC performance. So you've got bias current that's flowing, and so the lower the value of resistors, the less of an offset that's going to create. Lower value resistors give you less noise. And if you're working with a higher frequency filter, you'll want to have lower values so that parasitic capacitance doesn't impact your circuit design.
So I just wanted to jump in here quickly and show you how to make this resistor capacitor trade-off with our tool. So you'd go to the component selection screen, choose I want to choose open this accordion and adjust these resistors and capacitor slider. So you can see them changing here in the circuit. Then you can see the effect, say, on the magnitude as we change it, or say on the noise.
So that's 1 degree of freedom that we can use, and we give you the option of doing that trade-off. The other degree of freedom, which we basically just incorporate into the tool, is we set the circuit values in such a way that the amplifier doesn't have to work as hard. Or a more technical way of saying that is we keep the noise gain of the circuit down. And to explain this, imagine for a second that we don't have this amplifier here, and I'm just going to ground this. So imagine that, I've just got my circuit that looks like this, where this is R1, C1, this is R2, C2. And you can imagine if I had a relatively small value of a resistor here and a relatively large value of a resistor here, then I would get a fairly decent filter circuit because this second stage here wouldn't load this first stage because this would be much higher. This impedance of the second stage would be much higher than this. And the result of that is when you draw the response, you're going to get a relatively sharp peak. You won't get as sharp a peak as if you use an active filter, but you'll get a relatively sharp peak. But if you did the reverse, if you had high impedance here and low impedance here, then this would load the first stage a lot. And so now you're going to get this really, something, a peak, say, something like this or this. And so if you imagine that's kind of what you get before you add the amplifier. When you add the amplifier's job is to kind of fix this. The amplifier's job is to fix it so you get a nice, sharper peak than you can get just by using this passive scenario here. And so the more that you can start from a good spot before the amplifier has to do work, the less work the amplifier is actually going to have to do. And that's important. So if you can keep the noise gain of the amplifier down, that gives you 2 advantages. So one is you don't have to have as fast of an amplifier here, which means you can use a lower power amplifier. And the other thing is that you have a lower noise gain, which means that the noise of the amplifier and the noise of some of the circuitry here is going to be lower at the output than if you have to have a higher noise gain. So that's how we use the extra degree of freedom.